If you recall, this was a place where we paused yesterday. We were discussing about the information content, right? And the formula we arrived is I of xi is equal to minus log of pi, where pi is the probability part and I is the information content part, right? And this formula was given by Shannon. That was, I think, in somewhere around 1950. So that is why this formula is also called as Shannon information content formula. Okay. Are we comfortable till this part?
Yeah.
Awesome.
So one question, Ashutosh.
Mhm.
So far we have been doing a lot of theory, right? Like probability we did, and then we learned about the Shannon information content, and today we're going to learn about entropy.
Mhm.
So when we go into the real world and we start, doing this solving data science, deep learning problems, right?
Mhm.
Do we have to remember this theory background as well in the behind, or as long as we remember these important formulas that we are
Mhm.
going to apply, is that enough? Or we should always know, oh, you know what, this is a scenario of now Shannon information content is coming into picture. So will it be like that, or it will be mostly just application of these formulas?
Yeah. So to answer that question, Salman, so let me tell you, in real world, this theory will not be really helpful. Actually, we do have some framework, readily available framework that is open source. For example, we use PyTorch, we use TensorFlow. Using those framework, we just need to specify some of our input parameters. For example, if you want to design a neural network, right? So in that case, you do
Mm.
not need to know how a specific neuron operates, right? You just need to specify the number of layers you want. You just need to provide your input features, and you need to just do the training. Rest all it, the framework will take care, right? So in reality, the things are a lot simpler than this. The only
Oh,
reason we are covering this theory part is if you'll interview for any deep learning profile, right? These are the questions they are most likely to ask you,
correct.
because they are they can't give you a system, right? And they will ask you to design a neural network of 1,000 number of layers. It is pretty straightforward. So the
Yeah.
theory part help us to make an informed decision. For example, you know, we have the framework which will do all this job for us, but we need to provide input to those framework. You will have a framework, but the framework will ask you what kind of loss function you want to put in this framework. So you should know what are the different loss function option I'm having. We have covered square error loss, right? And now we are going to see the cross entropy loss function. So you should know that in this particular kind of problem, I should put this loss function, then my output will be very much reliable,
Okay.
right? So in order to make the informed decision, these theory is helpful, but definitely in case of real world, the things are a lot simpler. You will have the framework, you just need to put the parameters and play with it, right?
Okay.
Yep. But if you want to pursue from research perspective, then definitely these concepts are very important. Otherwise, your implementation will be limited to the work which people have already done, right?
Okay.
People have already provided some standard neural network. Most of the deep learning engineers, what they do is they just put their parameters in those predefined network and they try to get the answer. But it may not be very much useful for your use case, because every use case has its own story, right? So there may be situations where you need to tweak those existing architecture, and tweaking those existing architecture would require this theory knowledge.
Got it.
Okay. Yep. I know this theory is very, heavy part of it, but definitely trust me, after this week or maybe like after 10 days from now, what we will see is only the practical part. There won't be any lecture where I will be showing you slide. It will be real-time coding.
Okay.
Okay. Yep. But I'm just covering this concept so that if you sit for any interview, you would be able to answer the question. They are commonly asked questions. Okay.
Okay. Good.
Okay.
Yeah, I mean, so far, even the theory that you've explained, I have understood it. But I was just thinking today that because we covered so much of theory, right, that it may always not remain on top of our head, right?
Mhm.
So that's what I thought, that how does it, like in the real world, how it turns out.
Yep. Yep. Actually, one notion is created in the market, and that notion is a data scientist has to be a good statistician, right?
Yeah,
People,
that's why I read that a lot online.
yes, yes. So if by default any kind of interview you'll be sitting for machine learning or deep learning, they would expect you that you have good amount of knowledge with stats part, right? So doesn't matter whether you're sitting for deep learning or machine learning. These are the common questions you're definitely going to get. They will ask you questions about probability distributions, and you'll get all sorts of questions from descriptive statistics. Some of the topic we covered recently, right? From information theory. These are the most likely questions that you will be facing.
Okay.
Okay. Now coming to the content part. So today we will complete our binary cross entropy loss functions. And after today's lecture, you'll have two loss functions in your bucket. And I'll tell you when to use what loss functions, right? And this will be one step closer to building a niche deep neural network. Okay. Okay. So what is entropy? So if you have came across this word in your high school or college, entropy, very commonly people say that is a degree of randomness, right? This is the by heart definition I used to have when I was in high school, right? So but what is an interpretation of an entropy, right? Entropy, if I have to convey it in a layman term, entropy is nothing but it is an expected information that an event is providing. Okay. When I say expected, it means the average. Okay. In your screen, you see I have written a one paragraph that is enough to clear the concept of entropy. Let's not go into the definition part. Definition part is nobody's going to ask. We'll make a general intuition about entropy. So if you are doing an experiment, suppose you have performed some pool, right? Which political party is going to win these elections before actually the election happened? Okay. So after doing this pool, you'll get some information, right? Now, when you perform pool second time, immediately after 1 week, right? You're not going to get something new out of it, right? Because you have already performed the pool and you know the result, right? So what we say that the entropy in the second pool is lesser compared to entropy we had when we performed the first experiment, right?
And what kind of poll is that?
Election exit pool, pool means,
Oh, okay. Okay.
right?
Yeah.
Right now in India there is election festival going on, right? So people are
Yeah.
interested in performing this exit pool. In news you'll see that every news channel is flashing their own exit pool,
Yes.
right? So entropy is nothing but it is degree, or I should say it is a measure of unpredictability of the state, right? So
Yeah. So for example, now in, say, if in some exit poll, now let's say there are three political parties, and exit poll is saying that political party A is going to get maximum seat, then B is next, and C is next, right?
hmm,
So you're saying that the prediction that they are making, that's what entropy is.
no, not the prediction part. What I'm saying, it is
Mhm.
more related to information part, information content part. If you're performing pool for the first time, right, you're getting
Yeah.
some information,
Yeah.
right? If you're performing pool for the second time immediately after 1 week, you're not going to get something new. You have recently performed an experiment and you knew what was the information you had. So what I'm saying that in the second pool, the entropy
Yeah.
will be less compared to the first pool. The chances of getting the information is somewhat related to entropy. right? If you're reading a book, you're getting some information, entropy is high. For the first time reading a book, the entropy is high. If you're reading a book for the second time, same book, entropy is low, because the chances of getting something new again is lesser.
Yes.
Right. So that is how I would give you an intuition about entropy. That formal definition of entropy is nothing but, it's a degree of randomness. But I would suggest do not go with the definition part. It's a bit confusing. Okay.
But in the two scenarios they're explaining, where the first time I read, I got more information. The second time, chances I'm not getting more information.
Yes.
So in these two scenarios, what are you saying is entropy then? Like,
Entropy overall, it means that expected information or an average information. Right. So let me give you some annotation. Okay. Right. So you are having a book. Okay. You are reading a book. Right. And first time you got I1 information out of it. Okay.
yeah.
Second time you read I2 information. Third time I3 information. Right. Now I1 is greater than I2 is greater than I3. Do you agree with this?
Yeah.
Right. Now, what entropy is? Entropy is the expected information. Expected information means the average information. What is that average information? That is nothing but an entropy.
But isn't it also like this in case of a book, that when you read it a third time, you understand it better, so you extract more information?
Yeah. So again, here a lot of subjectivity is involved, right? If you read the book first time in a very well way, obviously in the third time you'll not get something new, right?
Yeah.
So what I'm trying to say here is, you have read a book very nicely. You have given good amount of time. You have understood everything about it. I1 is high. Second time when you read it, yeah, it was good. It was a kind of revision for you. You did not get anything new. It's just that it registered in your permanent memory. When you read third time, it was something that you by heart, right? So you're
Yeah.
not. So information content in first phase is highest, followed by second and third.
Yeah.
Right. So what is an expected information? Right. So expected information is nothing but it's an average information. Right. Now, please do not take this example literally, just to give you a feel. Entropy is mainly defined for a distribution. Okay. And in the previous slide, we have seen the formula of expectation. The formula for expectation was what? It was what? It was summation of xi probability of. Right. This was a formula of expectation. Right.
Yeah.
Now, here what we are having? Here we are having information part, right? So in the previous class, we have seen the formula for information. That was nothing but minus log of px, right? So just need to put this part here and you'll get this expression. This is a formula for entropy.
So entropy is product of
Product of, yes, p of x log of p of x. Now, if you literally look at this formula and try to interpret it, it is something like this. It is the expected occurrence of a random variable, right? But again, as I mentioned, that do not go with the literal meaning, do not go with the formula part, just try to create the intuition behind it, right? Just try to think at it is an expected information, right? And we know the formula of expectation is nothing but it is this. So you just need to put here the log of minus log of px in place of pxi.
Pxi is the probability of that event.
Yes.
Event xi, right?
Yes. Yes.
We are saying instead of probability of that event, we are putting log of negative log of px.
Yes, which is nothing but information content of that event.
Information content of that event. So for
Ashutosh?
example, in case of
Yeah,
book,
yeah.
I1 is the information content the first time, right?
Yes, yes. You have to replace, sorry, in place of pxi, you have to replace this xi part with minus log of px, right?
In place of xi or in place of pxi?
In place of xi.
Uh,
See, in the first read, in the first first phase, what was the, information you had? You had some information, II and PXI, right?
yeah.
Second, I2, PX2,
Yeah.
so on. It will go like this, okay? Now, overall, how much? You have to do summation,
Yes.
right? So that is from where I'm getting this formula.
Yeah.
So you understood how exactly we are trying to make a feel of entropy.
Here for log px is the base 2.
Yeah, here it is the base 2. Yep, definitely. See, do not worry about the base part, right? Base is something that will vary from problem to problem. If you are trying to calculate the entropy in information, then it will be a base 2. Right? But yeah, you were
Otherwise,
right. Yes, you're right. Here it will be base 2, but do not focus on the base part.
because if we write different base, then again answer will change, right?
Yes, yes. But you will not see any place where we are going to literally put values in this formula and trying to get the answer. It is just to give you a feel how the entropy, how to perceive entropy.
Okay.
Right. I'm just giving a different flavor of perceiving entropy. I know this is not something you'll find in literature. The literature meaning of entropy is something different, but those definitions, it will be very will make life very difficult if we want to relate it with deep learning concept, right? So you understood how this formula is coming. Is it clear to everyone? Zara, Nazma, Salman, Soumya?
I think to me it's still not clear.
Okay. Which part is not clear?
So I understood this part, right? Where you mentioned this I1 PX1 is the information in the first case.
Yeah.
I2 PX2 is the information. That's the formula for information. I understood that.
Hmm.
Then what you did, I didn't understand. To come to that entropy formula.
Yep. I'll tell you. And are you comfortable with this?
Yes, that's the information in 3 scenarios.
Yes. Right. So if I ask you, what is the total information that you're getting?
Summation of all of that.
Summation of all of this. Right. Which is what? Which is,
Yeah, I PX of I.
right. What is I? What is the formula for I we read yesterday? It was minus of what? Log of P.
P of X I.
Yes. Now you understood?
So the formula for I was log of PXI, right? Summation of log of PXI.
Yes.
So you
Yes.
replace that with, instead of I, you're replacing with that.
Yes.
So that's why you're having log P of X and P of X. Okay, yeah. Now I understand.
Right.
So yeah.
Now is it clear to everyone?
Yes.
Okay. Yeah. So this was really important concept. If you have understood well, really awesome. Because in one of my interview, this was the question they have asked me. Can you explain me entropy in a simple way? So now I think
Yeah,
you,
so we have understood the formula,
Yep.
but then when you are saying that in a simple scenario, the h equal to p of x into log p of x is the example of like the pole example that you gave, right? The first time it is, you know it for sure, like you have more information. The second time you have less, and then so on, right? So
yes.
what would you say again for entropy in this case, in case of this pole example that you gave? Like
So, yep. So what I'll say is, what is an average information you're getting through this entire process? That is nothing but entropy.
so the average information is going to be sum of all, right? So,
Yes.
sum of poles
Yes.
by, I mean, sum by 3. That's going to be
Yes.
the average, and that's going to be the entropy. Okay.
Yes. Yes. Now, see, now I'm having here one situation. Okay. So what, just think that I'm trying to solve a classification problem where my target variable can be only binary, right? So my y is some distribution of 1 0 0 1 0 like this. Okay, so this is my true label. Now I created one model with the help of sigmoid neuron, and I did some prediction. Okay, so here you'll have some probability value, right? It will be like 0.9, it will be 0.4, 0.5, 1.8, so on, right? So this is my true distribution, and this is my predicted distribution. Okay, now what I'm trying to do is I want to introduce another loss function. Okay, and that loss function name is called binary cross entropy. So from the probability concept, what we can do is we can find the difference between these two distributions, right? And closer these two distributions are, the better would be the accuracy of model, right? What I'm trying to do here is, if my predicted distributions become somewhat closer to my actual distribution, then this is the best case scenario for me, right? The closer these two distributions are, the better would be the accuracy of my model, right?
yeah.
Okay, so we need to have some metric that can, metric means metric, okay, metric that can find the difference between these two distributions, right? And lesser that difference is, better would be the accuracy of my model, right?
So for the, when you're talking about the difference here, you're talking about the literal difference between these values, right? Like
No, 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 no,
1
no, no,
minus 0.9, or based on the what threshold value you have, and then the y cap will change.
no, 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 no. I'm not talking about that literal one-on-one difference between this value. What I'm saying that the difference between the distribution, right? If I'll plot, so let's say I'm having a one distribution, right? And another distribution is somewhat like this, right?
And these probability distributions, right?
Yes, probability distributions, right? If I want to find the similarity between these two distribution A and distribution B, I need to do, some sort of a difference between these two distribution, right? And if the difference is 0, that means what, these two distributions are exactly identical.
Yeah.
But lesser that difference, the more closer A is with B, right?
Yeah.
Okay, so so for that there's a one term that is called KL divergence. So KL divergence gives us the difference between two distributions. Okay, and this is a formula for KL divergence, right? I'll not show the exact derivation of this formula, right? I'll just give you intuition how to perceive this formula. Okay, so this term you are seeing, this term is nothing but it is an entropy of my actual distribution. And this term you are seeing, this is the entropy of my predicted distribution. So what we are trying to do is we are just doing the difference between the entropy of my predicted distribution and true distribution. Okay. Yep.
Ashutosh,
Yes. Yes.
the for KL divergence, the first term is there, right? Sigma I is equal to 1 to n,
Mhm.
yi log yi cap. So yi should not be yi cap, or it should be only yi.
Here you are saying that yi cap, it should be yi
Yeah,
cap.
yeah,
Yep.
yeah.
I was about to come into that point. Yep. See, why it is yi? Because yi is the actual. You know, yi is the actual label. Actually, the thing is, this thing will get clear if I'll show you the derivation of this, but I don't want to go to the derivation part because I know that will not help you anywhere. For now, can you just, believe that this is the KL divergence formula?
Yeah.
And this is nothing but it is just, finding the difference in entropy between my true distribution and predicted distribution. What I can do is I can share one PDF with you that actually does this derivation. Okay. So
okay.
yeah, so you can go through that PDF, and if you have any question, you can ask me. That derivation is really long. That's why I'm not taking here, and I know that this is not something which will help you at anywhere. Right? Nobody is going to ask you the derivations of KLD. Like nobody asked to derive what is sine theta, what is cos theta, right? So in entropy, you can just consider this as a sine theta, cos theta, right? So these are the basic identities we have in information theory. So this is KLD, right? Now we want to minimize this term, right? We want to minimize this term, right? So see,
So that I think I missed in between. So the first one, the log y cap, right? So that y is y only, right? It's not y cap.
yes, it is not y cap, it is yi only.
Okay.
Yeah. So this is the difference between entropy of my true distributions and predicted distribution. Now any term which will minimize my this expression, it will also minimize my this expression, right? And here this is nothing but it is a constant. Why it is constant? Because I already know the value of y.
Yeah.
Right? So that is a constant. So any value of w and b which will minimize my this expression, it will also minimize my this expression. How? For example, you are having one expression x square plus 3, right? So this 3 is nothing but it is a constant. So what is the value of x that will minimize this expression? 0, right? The value of x equal to 0 will minimize this expression, right?
Yeah.
So obviously x equal to 0 will also minimize x square plus 3.
Yeah.
That's why from this we have reduced to this expression.
But from where did you get this? I mean, in third line you say loss equal to min WB W comma B KLD, and then suddenly in the next line you're saying min WB minus.
Yep. See, here I'm just putting the value of KLD. What is the value of KLD? This one.
Yeah.
Right. So here I'm just putting the value of KLD.
Yeah. You're putting the value there, but from in the first line where loss equal to min KLD, is there any relationship between, like, is it min WB dot K into KLD, or is it, what is the sign between min and KLD?
See, here this says that I want to minimize this KLD. I want to minimize this expression. So how do we read this is this? Find the value of W and B that will minimize this expression.
So that's how you're just reading it. Min
Yes.
WB means find find the value of WB which minimizes the KLD. That's what min
Yes.
KLD.
Yes.
Okay.
It simply says that compute the value of W and B that will give the minimum value of KLD. Right?
Okay.
So here I'm just putting the value of my KLD. and I'm just replacing it with by C, because here yi and yi is constant term. Yi we already know, right? So here it just became C. And now I can get rid of the C part, because any value of W and B which will minimize this expression, it will also minimize this expression. So my loss has effectively become this expression. Everybody with me?
But I understood it. But when you say the last part, right, loss equal to,
Hmm?
are you saying loss equal to min minus that whole thing?
No.
Is that thing minus that, or you're saying it is only the negative sigma y that part?
I'm just saying only negative sigma this part.
Okay,
What
okay.
this is just for reading purpose.
Yeah,
This
yeah, okay,
means
okay.
that the minimal value of this expression is what I want to be what I want to have as a loss.
Okay,
Minimize this
yeah, yeah.
expression.
Okay, it's clear.
Okay. Okay. Now from this expressions till this expression, everybody is clear, right?
Yes.
Okay. Now this expression is nothing but it is called binary cross entropy function. Okay. Now this can be further decomposed into two important parts, right? And that we can derive from here. See, this expression and this expression is same, right? Here I can take only two value, right? 0 or 1, because we are doing binary classification, right?
Yeah.
This expression and this expression is same.
Yeah.
Now what I'm trying to do is I'm trying to apply this into a binary classification problem.
Hang on. Didn't you earlier said that y cap is a distribution of, like, real numbers, 0.9, all of that?
Yes. What I said is y is always 0, 1, 0. It is a true label. Whereas my
Yeah.
prediction is what? It is a set of real number. It can be 0.6, 0.9, 0.8, like this. Now what I can do is I can convert this 0.9 in form of 0 and 1 by setting a threshold of 0.5.
Yes.
So I can binarize this value,
Yes.
right?
Yeah.
So now what I'm saying is now let us try to apply this into a problem of binary classifications where my y and y cap, they will be always take value 0 and 1,
Okay.
right? So this expression is reduced to this expression,
Yep.
right? Now I just want you to look into this bit carefully. This expression you can reduce to this expression,
Yes.
Yes.
right? And if you are with me till here, then this expression can be further reduced to this expression. See, what is my y0 cap? It is a probability of predicting a label as 0, right?
Yeah.
Which is equal to probability 1 minus,
Yes. Correct.
right?
Yes. Yeah.
This
Yes.
is reduced to this one,
Yep.
right? Okay. Now this expression can be further decomposed into these two equations, right? What if in case when my y is equal to 1, when my y equal to 1, then this part will get knock off, 1 minus
Yeah.
1, 0. And what? This y1 will become 1. So you will be,
Why
you will,
it will become 1?
yeah, y, because we are putting y equal to 1, right? So the value of this is what? 1. We will be left with minus log of y cap,
Yeah.
right? Similarly, if you'll put, let me remove this, there's a lot of clutter here. Yeah. If I'll put y is equals to 0, right? If I'll put y equal to 0, this expression will get rid of, because here y.
Yes.
So this expression is reduced to this one,
Why?
second,
Yeah.
right? Yep. So what I'm trying to make point here is this equation, this is the main loss function we will have when I'm having a binary classification problem. This expression is called binary cross entropy loss function.
What is it called? Binary?
Binary cross entropy loss function.
Okay.
Right? And you can decompose this formula further into two parts. One when your y is equals to 1, the other when your y is equal to 0. Right?
And what is theta?
Theta is nothing but it's a parameter, right? This equation is nothing, it's a parameter of w and b. And if you recall in the previous class, we have represented w and b by theta.
Yeah.
Right? This is the derivation of loss function, which is known as binary cross entropy. This is very commonly and popularly known as in case of binary classification problem, right? So now in the code that we have seen earlier, right, for sigmoid neuron, we can replace our loss function, which was initially square error loss, by this loss function. Right, so now you are having two options for as a loss function. One is square error loss that we have used in a sigmoid neuron algorithm. The other is this one loss function. Okay, I'll spin another bridge for 15 minutes immediately after this one. You can join and let me know if you have any question, any doubt into any of the things that we have discussed today. Right.